Right, so our reactors, that's the scale, so on the order of tens of cubic meters. And the temperature control is quite critical in these systems, right? Because our reaction rates are so sensitive to temperature, the temperature control being critical, they start to look like heat exchangers, these reactors. And there was this often cited rule of thumb that the reaction rate is often found to double for every 10-degree rise in the temperature, right? Can you imagine that? Just a 10-degree change in the temperature and the reaction rate doubles. And obviously that changes from reaction to reaction, but for many, many reactions, it's approximately on that order. Okay. So typically our reaction rates are in this range. And in this course, we like to comment also on the design-related aspects, the practical aspects of chemical engineering. So to heat things up is much easier than cooling them down. By easier, I mean the expense of the process. So implementing heating, especially getting you past ambient temperatures, right? Ambient around 25 degrees Celsius. So around 400 Kelvin. So going from 400 Kelvin to 800 Kelvin, it's all fine. It's not expensive to build a process like that. It's when you start going under even 373 Kelvin, when you start to need refrigeration, then the process expense starts to rise. So that's one of the things we look out for. And so with temperature control being so important, the thermodynamics of the whole system does matter as well. So here are some other views of reactors. So you can see in this case, this is the top end of a reactor. So this is this reactor sitting across multiple floors. And you can see that somebody's doing some work here on it. So all these connections, they might be for different things. There might be a main feed line here, for example. You might have venting ports. So if you're concerned that the pressure rises in the reactor, maybe you produce, maybe the number of moles of the product is more than the reactants. So the pressure could rise in that reactor, then you might need venting ports available. You might need ports for metering catalyst into the reactor, various things like that. So a typical reactor has all this kind of stuff on it, because quite quickly we'll be dealing with simplified views of reactors, right? Idealized views of reactors. We will come later on in the course to imperfect reactors and looking at more real-world reactors, but we are going to start with a very simplified picture of a reactor. And so that's why it's useful to just get an appreciation for what a real reactor looks like, all the kinds of metering that goes on. You can see some kind of motor apparatus up here. So that's probably some kind of stirrer that you are going to implement in that reactor. So quite a lot of power maybe to throw around. Maybe it's a powder bed of polymer or something like that. So that's what a typical reactor looks like. By the way, you can see something like a coil going around this reactor. So there might be some kind of temperature control going on here as well. And then coming to the conceptual view, quite often for our stirred tank reactors, we draw a symbol like this. There's some kind of mixer. So being able to get good contact is important to us, right? The reactions happen if the molecules can see each other. And sometimes the molecules that we want to react are in different phases. Sometimes we are trying to contact bubbles that contain some reactant with the liquid that contains some other reactant. So the contact, there's quite a lot of work to be done in terms of contacting fluids. So we might also have, we said about heat exchange being important. So this is a section through a jacket. So there might be a jacket sitting around our reactor, and we've got some coolant fluid that's flowing through that jacket. And then you can see we are feeding reactants in here. We might have some venting going on there. Here's your product overflowing down there. So these are all the types of things that we see around our reactors. Again, we said the reactors look like heat exchangers a lot of the time. And so here, I think we have yeah, here, let's see. It looks like in this picture, we've got our reactant flowing in here, and it's cold. And then it's flowing through these beds here. And if you zoom in on these beds, you can see they are packed with these particles. So these particles might be catalytic particles. And so the reactor is passing around them and reacting on those particles and hopefully giving us a product. And so the mixture of reactant and product comes out here. So when looking at these things, you start to realize a reactor is not some kind of magical thing. Just because we call it a reactor doesn't mean it's taking little molecules and going and doing, stitching them together or something like that. A reactor, by the end of the day, it's just a container, and we try to control the conditions in that reactor so that we get the effect that we want. So we might want we want to convert the reactants to products, right? So we control the conditions in that reactor such that we get that. So it might be that your reactant, it reacts, it forms a product, but then the product, maybe that starts to react with the reactants and give us something that we don't want. So we have to carefully control how long that fluid is flowing through that reactor. And there are a couple of ways to do that. One obvious one is just change the flow rate, right? So we can change how fast we are feeding that reactor. But the other thing we could do is also change the length of that of those tubes. So maybe this is 5 meters, and then we realize, well, if we go as long as 5 meters, then we start to get the unwanted products. So we need to cut back maybe 3 meters or whatever it is. So that's largely what this course is about, right? How do we design the space, right? This non-magical reactor, it follows the laws of chemistry and physics and all that. So how do we, if we know about the kinetics, if we know the rate at which things are reacting, how do we design a space that will maximize what we want, right? Which is as much product as possible, at as high a purity as possible, and as fast as possible. So, and all those three things might seem obvious. Yes, we want all those things, but some of those things might be in conflict with each other. Sometimes when you are reacting things as fast as possible, you might do that at the expense of the purity of the product. And then that will add to your mass transfer costs later, because you then need distillation columns or whatever to separate things out. So these are all the complications that we are looking out for as we design these systems. Any comments or questions so far? Right, and then we also have so all that is what we are trying to do, right? These nice design type of questions, very interesting stuff. So now let's just start with the basics, right? The reaction rate. By the end of the day, we need to know the reaction rate in that reactor. And so we are going to define here the reaction rate. And so this rate R sub I, we think of that as the rate of formation of component I. And the basis of this is moles per second per cubic meter, right? That's the default definition of a reaction rate. And there are other definitions that we'll encounter as we go. Sometimes the area matters in the reactor. So especially when you have little particles and the reaction is actually happening on that surface, then it's more area that matters, but there's a way to translate to an area-based view. So our default is on a basis of cubic meters. So just be careful with that. Whenever you are asked for a reaction, whenever someone says reaction rate, they mean moles per second per cubic meter. That's the default view of a reaction rate. And what I like to do is specify what component we are talking about there. So it's the rate of formation of component I. That's how we read that. And you'll often see, especially in the textbook, brackets minus R sub A. So when you say minus R, quite often we are talking about a rate of consumption, right? So most of the time, in fact, in the textbook, they refer to the rate of consumption of component A. So brackets minus RA, it's the same notation, right? Rate of formation is minus the rate of consumption, right? So that's the definition of the reaction rate. And the reaction rate itself is affected by two main things: the temperature, right? So the temperature, like we said, that changes the reaction rate quite sensitively most of the time. So temperature is one, and then the concentration as well. That's the other important variable, right? When you have things in your space, the more tightly packed they are, the more of these molecules that you have, then the greater the rate of collision, and then the more frequent the reaction. So the reaction rate, it's affected by temperature and by concentration. Right? Any questions or comments so far? Right, so if the reaction rate depends on those two things, then you see it's going to be affected also, or as a consequence, by issues of mass transfer, hydrodynamics. So how quickly can you get molecules to see each other, right? So if you like, these are knock-on effects. These are cascaded things, right? The basis is the reaction rate is affected by the temperature and the concentration. But that also means then that if, for example, your reaction rate is actually in the particle, so let's zoom in on a particle here, then there's a question, well, isn't there a concentration gradient? If my molar concentration here is one thing, then what's my molar concentration near the particle, right? The concentration right at the particle, that's what's going to influence my reaction rate. So even though if I measure the concentration in the bulk, I get some value there, that doesn't matter, right? The concentration in the bulk fluid is not what's driving the reaction rate. If the reaction rate is on the particle, then this concentration is what will determine the rate. And so that's why we say mass transfer then becomes an issue, right? Because the reaction rate depends on the concentration, then mass transfer is an issue for us. Hydrodynamics, that's another one. So if we have a well-mixed reactor, right? Let's say we are blasting the chemicals around because we put a stirrer in, and we get a good uniformity of concentration, we'll get a certain overall reaction rate in this reactor. If we have instead a long, thin reactor like this, and we'll see we call that a plug flow reactor later on, then you can imagine you have a high concentration of reactant in the beginning, but as we go, the concentration drops as that reactant reacts and disappears. And by the end here, we get a different concentration. So we can see that the reaction rate here is going to be quite different to the reaction rate here, right? So mass transfer, flow, all those things affect the performance of our reactor. Okay, and that's why you'll see quite a lot of computational fluid dynamics work where we try to estimate the concentration variation across the space. And then we've mentioned briefly, we have these different types of reactor. We just showed a plug flow reactor, then we get batch and mixed flow reactors. So in the batch case, like the name says, we react things in batches. We load the reactor up, we close it off, let it react, and then open up and take out the product. So that operates in batches. In mixed flow, we have a constant feed of reactants and a constant withdrawal of what we hope are products. And so that's a reactor in flow. And we may say, well, they should all be mixed flow reactors. But you see, it's easier to control things on a batch level. And we have some nice case studies that illustrate that. Okay, so that introduces general things in reaction engineering. Any questions or comments there so far? So, by the way, when you see me looking to the side here, it's this other screen. It's a big TV, so that's why I have to turn my head. Anyway, So we've defined the reaction rate. Then, of course, we've got the reaction stoichiometry. So here you can see in this example, 2 molecules of A react to give us 1 molecule of B. And then you have to be quite careful, if you are given the reaction rate of component B. So let's say you are told B is 50 moles per second being produced, then number one, the sign of that matters, right? So the rate of formation of B is 50 moles per second. And then quite often I see errors where we don't know how to deal with the 2 here. So if we want the reaction rate of A, the way to read this is that if we have 50 moles per second of B, then we need twice as many moles of A to react. So we need 100 moles per second of A. And of course, A is being consumed in that case. So RA is going to be minus 100 moles per second, right? Remember, R, the default definition is that it's the rate of formation. So we aren't forming A here, we are consuming A. So it's minus 100 moles per second. So that also takes you to the tutorial, right? You see in the tutorial, the first question here. So given this reaction, and given that B is consumed, in this case, B is a reactant. So given that B is consumed at this rate, what's the formation rates of A and C? So you've got these, you've got the setup in your system here. Sorry. So you saw I just had to chastise my son there for a second. Okay. So you've got your components. So component B is consumed at this rate. And by the way, it's written as a plus here because we have stated it's consumed at this rate. If we said it's formed at the rate of minus 150, then it would still be consistent, right? And by the way, when you approach these, you can check your answer. So let's just say we choose that randomly. So you can check your answer. It says that answer is not worth anything. So it gives you the solution to that there. So the correct answer here is minus 150. So because it asks for the rates of formation of A and C. So B is consumed at 150 moles per second. So A will also be consumed at 150 moles per second. That means it's formed at minus 150 moles per second. So that's A. And then we form twice as much C as A is consumed or B is consumed. So we'll produce plus 300 moles per second of C. So that's there, right? So that was the answer that we were looking for. And then, by the way, if you click try another, it's going to change the numbers in the question, and you can try that again, and you can check again. So, so yeah, as you click try another, it's going to change the question there. Okay, so you can practice with that, and yeah. So that's stoichiometry. And so that's the most general way to work out the relationships between the rates of things. Maybe also to say that you can see there is just one reaction event here, right? All these species, A, B, and C, they're all reacting in one reaction. That's one reaction that's shown there, okay? But we can define rates for each of these. So one reaction, but 3 rates. There's a rate of formation of A, rate of formation of B, rate of formation of C. So we can define rates on the component basis, even though we have one reaction. Okay. Right. The other thing we should note here is that the mass has to be preserved in a chemical reaction. So in this course, we'll be looking at chemical reactions, not nuclear reactions. So in a chemical reaction, we are rearranging the molecules, or we are changing the structure of the molecules, which includes breaking them into other molecules also. So that's all true, but the total mass has to be preserved then. If we are simply rearranging the atomic centers, then the total mass on the left must equal the total mass on the right-hand side. And so we can say that the net mass change in a chemical reaction is 0. And it's written in this strange mathematical way, because we here are estimating the mass of one event. So nu I is the stoichiometric coefficient of component I. So nu A is -3, nu B is -2, nu C is +2, right? So the stoichiometric coefficient, it's negative for reactants and positive for products. I know you know all this. I know in chemistry and even in high school, you already know all this stuff, but we are, in a way, for completeness, we are saying it again here. So if you look at this reaction, we can count the mass involved in this reaction. So we can say 3 moles of A react. So if that's moles and then molar mass is kilograms per mole, then this is an estimate of the number of kilograms if 3 moles of A react. So it's going to be -3 times the molar mass, and then -2 for B, and then +2 for C. And the net effect of all that is 0. We are not net producing any mass here. We may be changing the number of moles. We are changing the number of moles in this case, right? We have 5 moles at the beginning and 2 moles at the end, right? Per cycle of reaction. So here we are getting fewer moles. The number of moles is dropping, but the amount of mass is staying the same. Any questions or comments there so far? Okay, so that's, and then here, reaction rate and reaction speed, right? We talk about rates in reaction engineering, and that in effect is about how many times something happens, right? So how many times does this reaction happen so that we eventually get a certain number of moles coming out at a certain rate? So that's a rate. It's not quite the same as a speed, right? A speed relates more to how much time it takes for something to complete. So if you think about velocity, how fast are you, how much time will it take you to complete 1 meter, right? So a speed is a different thing to a rate. A rate is more about how many times does something happen. And it's useful to keep an awareness of that, because it does come into many developments that we'll see as we go. And then we've said this before, the reaction rate is a strong function of temperature, and it's a function of concentration. Right, and if we take an example, maybe it's kCa to some power here, and then the constant K, that depends on the temperature. It's related through the Arrhenius expression, which has 2 parameters, the pre-exponential factor, so-called pre-exponential factor, and the activation energy. R, of course, is the universal gas constant, and T is the temperature. So we'll just mention that for now. We'll be looking at that in a lot more detail when we get to the heat transfer side of things. And then you can work through this example. So you've got your species reacting here, and then we can relate the reaction rates to each other. So the rate at which sulfur dioxide is consumed can be related to the rate at which oxygen is consumed. So like we said earlier, a rate of a component divided by its stoichiometric coefficient is equal to the rate of another component divided by its stoichiometric coefficient. And so you can apply that right the way through. That applies, that's easy in the case of a single reaction. We do have cases where there are multiple reactions, and then it's more complicated, because these rates are typically the net rate. So the rate of consumption of A due to all the reactions it participates in. In that case, you can't so easily write out an expression like this. For now, we'll stick to single reactions. We'll address multiple reactions as we go. Then elementary reactions, again, I expect you'll have covered this in much more detail in your chemistry courses. But in an elementary reaction, the reaction rate is given by the product of the concentrations raised to the stoichiometric coefficient. So this is a nice general view that we can take. In fact, maybe let's just do a quick example of something like this. So let's say we have 2A plus 3B going to, let's say, 5C. Of course, in some simple reactions, we don't often get such high stoichiometric coefficients, but I just want them to be different so that we can see so we can see the effect here. So the reaction rate here, let's say we are interested in the reaction rate of component A. So that's going to be the kinetic rate constant multiplied with the stoichiometric coefficient, multiplied with the species concentrations. So here it's going to be C sub A raised to the power 2 times C sub B raised to the power 3. Now, this reaction is not reversible. So the reaction rate will only depend on these species, right? If it is reversible, then we also have to include the influence of the reverse reaction. So let's make this reversible. See, I need the arrow. I can't recall the code for the backwards arrow. So there's the upright. So let's say that's reversible. And let's say the forward reaction. So forward reaction constant is AF, and reverse is AR. Then our net reaction rate, so minus RA. So A is consumed in the forward reaction, so it's going to be K sub F times CA raised to the 2. And component B is also reacting here. Right, so A is consumed in the forward reaction. We have written the reaction rate as a consumption rate. So A is consumed in the forward reaction here. So that's why I'm leaving that as a plus. And then A is produced in the reverse reaction. So because we are working as consumption here, we need to say minus, and then K sub R. And then the reverse reaction rate is 5 C's going back here. So we are going to say here C raised CC raised to the power of 5, right? So that's how we get the rate expression, right? We call these reaction rate expressions. So the value of R is the rate itself, and then this term we regard as the expression. So it's the expression by which we can calculate the rate itself. So that's the reaction rate expression. So in the case of the irreversible reaction, that's the reaction rate expression. In the case of the reversible reaction, that's the reaction rate expression. Okay, so those are elementary reactions. Okay, and then again, you can try this out in this tutorial. So there's an example of that. And then this question is also making a point of the units for K. So you see here in this example, we have these constants, K. And if you think about it, K does not have fixed units, right? If you look here, RA has fixed units. We said moles per cubic meter per second. Those are that's the default definition of the reaction rate. And then concentration, of course, that has fixed units, right? Moles per cubic meter. You can't do anything about that. So the units of K are necessarily not fixed. And it's a little bit surprising because it's such a fundamental thing, right? You would say, well, K relates to the thermodynamics and it relates to how the molecules are interacting. So it ought to be fixed, but it's really not, right? Once you write out your rate expression, it's obvious that it can't be fixed, right? R is fixed, C is fixed, so K can't be fixed. K is going to depend on these stoichiometric coefficients. And so we can say that the units of K, so I use square brackets for units of K. So the units of K must equal the units of R divided by the units of C sub A raised to the 2C sub E raised to the 3. Okay, and so moles per second per cubic meter divided by moles per cubic meter all squared times moles per cubic meter all cubed. And that's how you work out the units there. So you can see that in this example. So you've got nice high stoichiometric coefficients, and all of that is described here in this example. So you can work the units out like this. There are the units of the reaction rate, and then here you've got the units of concentration, now raised to the power of the stoichiometric coefficient, and so that's how you work them out. So you can get some crazy coefficients here, meters to the minus 27, you can see in this case. Okay, so work through those examples. And right, so reversibility, equilibrium, and so on. We'll come to these topics in the material for next week. Then for the material for next week, there is another Publon out. So if you go to Publon ID 71, you'll see for our general mole balances, right? We'll introduce these topics next week. The general mole balance is like that, the batch reactor balance, and I'll be building in examples and tutorial questions into these Publons as well. Okay, any questions or comments before we go there? So I must say, you know, you want to engage, you want to speak up and ask your questions. Yeah, I think nobody has said anything during this whole session, right? So we'll be looking at some ways to get a bit more interaction going as we go. All right, so I guess that's it for today, and I'll see you next on Wednesday.
Thank you, sir.
Thank you.